First-order linear differential equations are differential equations when x and y are inseparable. And they are solved using the integrating factor method. With the integrating factor, which is symbolized by the Greek letter mu. In order to use mu, we have to make sure that the differential equation is in this format, or must be able to be manipulated to this format, or else we will not be able to use the integrating factor method. I'm going to teach you how to solve first-order linear differential equations. The first thing we do is multiply the whole equation by mu. We will state that the derivative of mu is mu times p of x. Now we will find the derivative of mu times y via the product rule. Remember this equation? Good. Now we will substitute this equation into the product rule, and you see that we get the derivative of mu times y is mu times q of x. Now we use the process of solving first-order separable differential equations to solve for y. First, we multiply both sides by dx, and then integrate both sides. This gives us mu y equals the integral of mu q of x dx. Then we divide both sides by mu to get y equals 1 over mu integral of mu times qx dx. Now you are probably wondering what mu is. And no, it is not the most powerful being in the universe. Do you remember when I said that mu prime is equal to mu times p of x? Well, with this equation, we can find what mu is using the first-order separable differential equation process. First, we separate our variables by dividing by mu. Then, we integrate. Because we want mu all by itself, we make use of the property ln always cancels, and make both sides powers of e. This leaves us with mu equals e to the integral of p of x dx. In our first example, we will have both an equation and an initial condition. First, we need to get this equation into the proper format by moving the negative 0.196y to the other side. 0.196 is p of x, so mu equals e to the integral of 0.196 dx, which is e to the 0.196x. Our q of x is 9.8, so we substitute everything into our y equation. Then I took the 9.8 out of the integral and integrated e to the 0.196x. After moving some things around, we get the equation y equals 50 plus e to the negative 0.196x times c. Using our initial condition, y of 0 equals 48, we can solve for c, and you see that we get c equals negative 2. And our final equation is y equals 50 minus 2 divided by e to the 0.196x. For a second example, we will again have an equation with an initial condition. The first thing we do is divide throughout the equation by 3, and we see that mu will be e to the 5x. We then put everything into our y equation. Our q of x is 8e to the 3x, and we combine that with mu to get 8e to the 8x, and then we take the 8 out of the integral, and take the integral of just e to the 8x. We do some rearranging and solve for c, and get negative 3. Our final equation is y equals e to the 3x minus 3 divided by e to the 5x.